Oh, thank you very much. Actually, I just moved to Berlin, so I'm sitting in my own apartment in Berlin. So due to a lot of complicated reasons, unfortunately, I cannot be there in Cambridge. But I hope I will see you soon in person. So today I will talk about high-order convergence of the PML method for periodic surface scattering problems. So this is the outline of today's talk. There are three parts, actually it's two parts that is scattered by periodic surfaces in 2D and also by bi-periodic surface in 3D. But I know some part of you already know this work, so I will keep that short. But this is still a necessary part for the second part, so it is. I will also introduce that in case not everybody knows that. So let's begin with the problem in 2D. So this is the mathematical physics background for the problem. Given a periodic surface gamma, which is a graph of a periodic function. So we assume that gamma is sufficiently smooth just to avoid any complexities that caused by the singularities. So for simplicity, we also assume that gamma, the surface, is impenetrable. So if there is an incident field comes from above gamma, it cannot propagate through the surface. So the wave, it is scattered by gamma, and the scattered field, it only exists in the half space above gamma. So the domain above gamma is called omega. So this is a periodic domain, periodic in x1 direction, but in x2 direction, it is unbounded from above. From below, it is bounded by the surface gamma. So this is the domain and the surface. Then given an incident field ui from above gamma, it is scattered by the surface and produces the scattered field us. Then us satisfies the Helmholtz equation in omega, with k the real positive wave number. And we also let us satisfy this Dirichlet boundary condition. So just this is an example. So we may also consider other kind of boundary conditions. So this is just one example. But we need this boundary condition to make sure that with this boundary condition, the problem is well posed. Moreover, for a scattered field, we always need that it satisfies a proper radiation condition to guarantee that the scattered field, it is unique and physical. So this is a physical problem, but from my point of view, I would like to consider a more general mathematical model. So we just reorganize these stuffs to write that in a more mathematical way. So we assume that the total field U, it satisfies the Helmholtz equation with a source term F. So omega H is a domain between gamma and gamma H. So the support F is here. So it is compactly supported in omega H, and U equals to 0 satisfies the Dirichlet boundary condition on gamma, and the propagating radiation condition is written as here. So this is given by a detour map. And your height here is a Fourier transform for U on gamma H. So this is a general mathematical model we want to talk about. And also here we make sure here we only require that F is in L2, but we still assume that it is as smooth as we want, just to make sure we don't get into stuck with other complexities. So for the unique solvability of the problem, as I said that this boundary condition is only one example. For this boundary condition, the unique solvability has already been proved in these two papers. The first is in the standard Hilbert subleft space H1 omega H, and also in the weighted subleft space. So that's why I find that we don't need to worry about the unique solvability of the problem. So the rest of the problem is to how to solve this problem numerically. So let's begin with the first part, the perfect match layers. So this method is well known to truncate the scattering problems. So for this problem, what we do is to add a absorbing layer above the surface gamma H. So the layer is the thickness of the layer is lambda. So this is the upper boundary of the layer. So this is a gamma H plus lambda. This is the PML layer. So within the layer, the wave is absorbed very fast. So on this surface, on the upper surface, the wave is absorbed very fast, so it almost vanishes. Due to this fact, we approximate the problem by a new one. So the new function, your tutor is a new function. It satisfies the new equation. So capital L, it is a new differential operator within the layer gamma omega H. Below the layer in omega H, capital L is the same as the Helmholtz equation. So it is the same. So this is the physical domain. But above the surface, within the layer, it is different, defined by the function S. So the function S, it describes how the wave is absorbed. And U tilde, it satisfies the Dirichlet boundary condition on gamma the same as U, but U tilde is approximated by 0. So we give U tilde equals to 0 on gamma H plus lambda because the wave almost vanishes. So the approximation we set is to be 0. So we get a new problem that exists in the domain between gamma and gamma H plus lambda. So we call that omega H plus, this should be lambda, sorry, this is lambda. So we approximate the problem in the strip, periodic strip, omega H plus lambda. So this is the way we add the perfect match layer. Since U tilde is an approximation, the key question here is about the convergence of U tilde. So so the key question here is about the convergence of U tilde to U in the physical domain omega H. So first, we since the new differential equation capital L, it has a very clear form which only depends on x2 in this PML layer. So we can also use the detour map on gamma H to rewrite the problem in the domain omega H. So we can see that U tilde, it satisfies exactly the same equation as U in omega H and the boundary condition on gamma. But on gamma H, it satisfies a different boundary condition due to a different detour map. So this is here. In the exact formulation, the blue term does not exist. Or in another word, it is said to be, for example, it is 1, the constant 1. So this is the only difference. And here, sigma is defined in this way. It is called the PML parameter. So you can see that sigma is related to two facts. The first one is the thickness of the layer. So still this is lambda, sorry. So it is depends on the thickness of the layer. Also depends on the function S. So the parameter rho. So sorry. So it depends on two parameters, the thickness lambda and the parameter rho. But we don't want the PML layer to be very thick. Then the computational domain is too large. Or when rho is very large, which means the function has a very large derivative. These two things we don't want. So we expect the convergence such that we don't need a very large sigma to make sure that U and U tilde are also very close. So here I list two, although for this method, there are many papers related to the topic, but I only list two very close ones. And also these two papers that motivated my work. So the first is in 2003 by Chen and Wu. So they consider the quasi-periodic case, which I will briefly introduce later. So they said that except for a finite discrete set of quasi-periodic problems, the convergence is exponential. And in 2009, in this paper, for a general rough surface problem, they proved that the convergence is 1 over sigma. So you can see that this convergence is really not that fast. But in their paper, they made a conjecture that actually in any compact subset D of omega h, the convergence is exponential. So this make me curious about the result. So that is also the motivation of my work. So then let me introduce the convergence analysis for the case in 2D. So let's recall the problem. This is the original problem. The solution is U. So this is the solution, the exact problem. And this one is the approximation by the PML, and the solution is U tilde. So we have the same, exactly the same equations in omega h, and the same boundary conditions on gamma, but you can see that the detour map on gamma h, this is different. So the factor here is something extra from the PML. So to deal with these problems in the periodic domain omega h, I have to introduce the very important tool, the Floquet-Bloch transform. So here we have a function phi, which is compactly supported and smooth in omega h. Omega h, I recall that it is an infinite domain in x1 direction and also periodic, but bounded in x2 direction. Then we define the Floquet-Bloch transform as this infinite series. So you can understand that as a generalized Fourier series. So instead of the normal Fourier series where the Fourier coefficients are numbers, here the Fourier coefficients, they are functions, but the functions are repeated. They are repeated periodically. So this is the definition of that. So after the transform, we get an extra parameter alpha. But so alpha lies only in a boundary domain between -1/2 to 1/2. And here x, the function, the variable which original lies in omega h, now it is in one periodic domain, omega h2 pi. So this is the definition of omega h2 pi. So it is restricted in one periodicity cell. Here are the properties of the transform. First, when alpha is fixed, the function is alpha quasi-periodic. So if you translate the function to 2 pi in xy direction, then you get an extra factor here. So that is alpha quasi-periodic. And the inverse transform is given in this very easy form. So this is given by the integral with respect to alpha in this boundary domain. So this is the inverse transform. Moreover, in this operator, it commutes with the Laplacian operator. Now we are prepared to apply the transform to the original problem and this PML approximation. So we apply the transform to both of the problems, and then we compare the problems we have after the transform. So suppose W and W tilde they are transforms of U and U tilde. Then U and U tilde, they are the inverse transform of W and W tilde. But here, I only give that in one periodic cell. So this is the integral is a little bit easier compared to the previous page. So what are the equations for W and W tilde? So we consider the case when alpha is fixed. So when alpha is fixed, the problem is alpha quasi-periodic, and then they satisfy the following equations in one periodic cell. First, they satisfy the same equations, still the same equations in omega h2 pi. And on gamma 2 pi, and they satisfy the same boundary conditions, but on gamma h2 pi, which is gamma h restricted in one periodic cell, the detour maps, they are different. So these are different detour maps. So you can see that the hyperbolic cotangent function in the original detour map, it comes here. So if we want to compare U and U tilde, it is natural that a natural idea is to compare W and W tilde for each fixed alpha, since alpha only exists in a bounded domain. And since W and W tilde, the only difference here is the detour map. So a natural idea is to compare the difference in the detour maps. So the difference in the detour map is written as this function f alpha g sigma. So this is the difference between these two functions. It depends on alpha g and the parameter sigma. We want to consider the convergence with respect to sigma. So we get back to the two references I listed before. So in the 2003 paper, the authors made the assumption that alpha plus g, the absolute value is always not equal to k. In this case, they had the convergence analysis that this function, it converges exponentially with respect to the absolute value of sigma. But in the 2009 paper, the authors considered a more difficult case when this absolute value is close to k. Actually, when it is equal to k, the convergence rate is reduced to 1 over sigma. So this is the reason why in this paper the convergence is only obtained. This convergence is obtained. So this it seems that the case that when alpha plus 2g for this alpha, when alpha plus g, the absolute value equals to k, it is very difficult. So the main idea for my work is to avoid how to avoid this alpha when the absolute value of alpha plus g equals to k. So let's begin with this idea. So first, we want to find out all these alpha such that this holds. However, to make sure this works, we have to assume that 2k is not an integer. So in this case, k can be written as a fractional part kappa, which is minus half to 1/2, but not 0, plus a constant g. Then in the interval between minus 1/2 to 1/2, we have these two difficult points, minus kappa and kappa. Then we recall the boundary condition that W alpha for the detour map, we have this term, which is the square root. Then we can use the Neumann series to conclude that when alpha is close to minus kappa, so close to this point, it can be written as a W1 plus alpha plus a square root kappa plus alpha, W2 plus alpha. So both W1 plus and W2 plus, they depend analytically on alpha. So it only has this kind of square root singularity. So when alpha is close to kappa, it is the same. So you can also define the square root a little bit different, then we can see that we can we redefine the square roots, then we can extend W analytically in a neighborhood of this interval minus 1/2 to 1/2, except to these two red rays. So these two red rays, they are the singularities, they are the branch cuts of the square roots here. Of course, W tilde can be extended in the same way, but much easier because it is analytic on alpha. So we have already extended W and W tilde on alpha, and recall that we had the problem of the W at kappa and minus kappa. Then we can use Cauchy integral formula and also the continuity of the function near kappa and minus kappa to avoid this integral along this near this point. So we replace the integral contour from the line segment minus 1/2 to 1/2 by C0, which is a purple curve like that. So we go through a straight part, then the lower half circle, and then the upper half circle. So from the Cauchy integral formula, we can get that U can be written in this form, and U tilde also in the same way. It is also written in the same way. So now we have already rewrite the integral on the curve C0. Now we can continue with the part we original planned. So first we consider the convergence of this function, capital F. So we prove that the function converges exponentially, and this convergence it holds uniformly for all these alpha on C0, and also for all the g, the integers. Then from the convergence of the function f, the detour map it also holds uniformly, and also then we can easily get the convergence of W tilde to W, and this also holds uniformly for alpha. Finally, from these two representations, we can easily get that for any compact subset D, the convergence of U tilde to U is exponential. So this is the result that I concluded here, and the convergence is exponential, and we can also show that in this picture. So here you can see that I take these 4 examples from k to equals to 1, 1.2, 1.5, and the square root of 5 here. So interestingly, in my proof, I have to exclude the case that when 2k is not an integer, but in this paper, in this picture, it seems like that k equals to 1 and k equals to 5, which are the case that is not included, they also converge exponentially. But maybe this is not true because maybe from numerical point of view, when the error becomes slower, we can see something different. So Wang Tao is also here. If you want to ask him, I think he will explain more. And this is a 2D case. Now I will move on to the 3D case. So 3D case, then the gamma is no longer the curve in 2D, but a surface in 3D. So this is a graph of a biperiodic function. Then we have the half space above gamma, also denoted by omega, and the problem is almost formulated in the same way. So we still have the source term f, which is compactly supported in omega h, with a boundary condition and the detour map. However, now we have to use the vector c to replace the previous scalar valued one. So the difference is between the 2D and 3D problems are the detour maps. So you can see that in 2D, this is the detour map is given in this way, where C is in R, but now the bold C is in R2. So as for the 3D case, we still apply the Floquet-Bloch transform. So for the Floquet-Bloch transform, we have also the same similar here. We have the different detour map where alpha and G, they are in 2D. So recall that in the 2D we made this assumption here alpha plus G. So for the 2D case, we noted that the difficult points are when alpha plus G equals to K. And this difficulty also holds in 3D. So that is the norm of alpha plus G equals to K. In this case, it is still difficult. So recall that for 2D case, we made the assumption that 2K is not an integer to avoid these difficulties. So for any K, positive valued K, we have these two critical points, minus kappa and kappa. When K is not 2K is not an integer, minus kappa and kappa are two different points. But let's see what happens for 3D. For 3D, we have alpha plus G equals to K, but so you can see that all these alpha, they are located in the circles with center minus G and the radius K. So here are some examples in 3D. For when K equals to 0.4, fortunately in only one cell so I had to claim that after the Floquet-Bloch transform in 3D, alpha is in minus 1/2 to 1/2 square, so in a square. So this is the square where alpha lives. So we have to do the integration in this square. So for K equals to 0.4, fortunately we have this only one circle with center 0 and radius 0.4. But when K equals to 1, in this square we have this picture, and K equals to 1.4, it looks like that. So very complicated. You can imagine that when K gets larger, it becomes more and more complicated. So there is no way that we can avoid these points. So in 2D cases, we just made a simple assumption that 2K is not an integer, then everything is fine. But for this case, if we want to get the same result, we have to make sure that K is smaller than 1/2. So this is a very strict assumption. So we don't want to only to deal with such easy cases. So we also want to consider these two cases. So we have to so in this case we have to deal with these cases. So any point alpha 0, so the critical points, they are lying on the red curves. So alpha in here, they are on the red curves. So for each alpha 0, we define the set G. So the set G, so it denotes the index of the curve that passing through alpha. For example, when alpha is here, there is only one element in capital G. But when alpha is here, there are 4 curves that passing through alpha. So there are 4 elements in G. So this is a notation. To deal with the problem, here I have to make it very abstract, unfortunately. So we have to define the operators. So we have to write this square root separately. So the original equation can be written in this way. So A alpha is the part without the singularities, without these terms, and BG alpha, they come from the detour map. And from the W tilde, it comes from the PML solution. So it has this hyperbolic cotangent term. So you have to compare these two terms. For simplicity, we rewrite this quite long term as H alpha G sigma. Then we can use Neumann series to rewrite W and W tilde in this way. So this comes from the Neumann series. The main idea here is just to compare these two functions term by term. So let's begin with the easiest case, which is almost the same as the 2D case. In this case, when k is smaller than 1/2, we have only one element in G. So everything is almost the same as the 2D case. So I want to go through quite fast. So we use the polar. So first I have to we use the polar coordinate to write alpha as REI theta. So in the yellow domain, this means R is close to K. Outside this yellow domain, from the 2003 paper, the convergence of W tilde to W is already exponential, so we don't need to worry about that. We only need to worry about the is the part that lies within the yellow part. So we use the polar coordinate first and then write the integral as two parts. So the integral, it is from first it is in the square, then the blue part, the green part is when it is outside the yellow domain. So outside the yellow annulus, then this is good, but within the yellow annulus, we write it as a polar coordinate. So for this part, from this 2003 paper, we already know that it is very fun, very nice. So the convergence is exponential, but the width of the annulus, we call that the delta. We have to make that exact because we will use that later. So we have the we already have the exponential convergence in the part outside the yellow annulus. Then we have to deal with the red part, which is within the yellow annulus. So recall in the previous page, we used the Neumann series. We have these expansions, which is in a very much easier form. And then we do the same thing. So still they have the square root singularity. So we still extend the solutions with respect to R. So we only so here we consider that for any fixed theta, when theta is fixed, we extend Wm and W tilde m with respect to R to the lower half disk near the value K. Then we extend that to the lower part, and then we can do the same thing to replace the integral by the line segment here to the lower half disk K, let's say. Then use the same argument, we can show that the convergence of W to W tilde, W tilde to W here is exponential with respect to the radius delta. Then finally, we can conclude the result that in this case, the convergence of U tilde to U in any compact subset is exponential. So this is the easiest case. Then I will go to the much more complicated cases. So as I said before, so when the element of G is always 1, it is easier, but when it becomes larger than 1, it is much more complicated. So I only give the example when the number then there are 2 elements within G. So for example, there are 2 annulus passing through the same point. Then so here I have to show record that here. Then there will be 2. So here there will be more than 1 element like that happens here. So that is why I read the formula here. So we have to consider the convergence of this function, which have more than 1 terms of square roots. So the idea is very natural. I have to compare this, consider the convergence of this this function just directly. So the main point is we choose delta. So delta is the width of this annulus. So sigma is a PML parameter. We choose delta to be sigma to the -2 gamma, where gamma is any value between 0 and 1. Then the function it decays. It converges as sigma to the minus gamma m plus 1 plus n, where m and n they are greater or equal to 1. So since we have to do the integral, so the integral domain M, it is the intersection between these two annulus. So the area is about sigma to the -4 gamma. Then finally, we can conclude that this integral is converges as sigma to the minus gamma m plus n plus 4. Then finally, we combining other terms, for example, this single annulus and also the exponential in decaying parts. We conclude that this integral it converges. Sorry. So we have other terms. So when m and n, one of that is 0, other term the convergence is -6 gamma. Then considering the other parts, the single annulus or the part without annuluses, then the convergence of u tilde to u is sigma to the -6 gamma. So this is the result for the more complicated case. So here finally I can conclude the results for 3D. So for 3D cases, the convergence it can be so this is the greater or equal to 0.5. So for in general for these cases, the convergence is -6 gamma, where gamma is can be any value between 0 and 1. For 2D, because I made this in the previous part, I made the assumption that 2k is not an integer, but when 2k is an integer, we can use the same way, and what I can get is that the convergence is -4 gamma. So very interesting. So this is, at least theoretically, I can get that, which is worse than the 3D case. But I have to say sorry here because I cannot show you the numerical results because for the 3D case, if you use the finite element method, it seems that we cannot see the convergence of the PML because the finite element error is already too large. That it covers the error caused by the PML. So we have to just stop here with this theoretical results. So the conclusion. We conclude that, so at the beginning, I mentioned the conjecture in the 2009 paper. So I conclude that this is the result I obtained at present. So for the cases, for some special cases, for the periodic surfaces, we can get the exponential convergence. For the 2D case, when 2k is not an integer, and for 3D, when k is smaller than 1/2. So the main idea here is to change the integral contour with the Cauchy integral formula. But for the other cases, when for example in 2D, when 2k is an integer, or 3D k is greater or equal to 1/2, we cannot get the exponential convergence. I don't know if it still holds or it is not true, but as far as I know, I can only get the following results. So for 2D, it is a little convergence slower than fourth order, and for 3D, this is sixth order. So that's all for my today's talk. Thank you very much for your attendance. Yeah. Mm-hmm. Okay. Actually, in from numerical part, I didn't do anything to change the integral contour. I just use the integral contour from -1/2 to 1/2. So the line segment, nothing special there. Yes, what you do is only need to have a higher order quadrant rule, then everything will be just fine. So at first I thought, as you said, I also did that to reform the contour, but then later on I discovered that I don't need to do that. The result is exactly the same. I remember that I tried to use the Neumann value, but I can't see much difference. So I have done that some time ago, then, but I think it is quite similar. So my yeah, this is what I got. I think for 3D, I also consider the Neumann boundary condition, and the result is the same. Oh no, gamma. No, I didn't consider that. But for gamma, I don't think it is that. I don't know if the uniqueness still hold. Mhm. So but for the case with propagating modes, I'm still considering that. I think maybe this is similar to what you mentioned. Think- Hmm. You mean there is an obstacle there? I think it depends on the incident field. If there is an obstacle, I think if there is a plane incident wave, it will be very different. But with a point source, may be similar. Thank you. Bye bye.